नमस्कार, मैं आनंद कुमार खत्री। आज के हमारे लेक्चर का विषय है एटमॉस्फेयर, पार्ट 5, एक्स्ट्रा ट्रॉपिकल cyclones. Poleward of the subtropical regions, winds in the lower troposphere tend to be southwesterly in the northern hemisphere and northwesterly in the southern hemisphere, again owing to the Coriolis effect. Since warm air is being moved poleward at low altitude, the wind flow is no longer associated with the direct heat engine of the Hadley cells. Instead, the continued transport of heat from the equatorial trough towards the poles is facilitated by large low pressure eddies called extratropical cyclones. These phenomena develop along the polar front, which separates colder polar air from warmer tropical air. When sufficiently large temperature differences occurs across the frontal boundary in the lower troposphere, the intensity of this temperature gradient is referred to as the boroclinicity of the front. Extratropical cyclones have three stages of expansion: the developing stage, in which an undulating wave develops along the front; the mature stage, in which sinking cold air sweeps equatorial west in the surface. Low pressure center and ascending warm air moves poleward east of the cyclone, and the acute stage, in which the warm air is entrained within and move above the polar air and becomes separated from the source region of the tropical air. Cyclones that progresses no further than the developing stages are referred to as wave cyclone, while extratropical laws that reach the mature and accumulated stages are called boroclinically unstable waves. Extratropical storms development is referred to as cyclogenesis. Rapid extratropical cyclones development, called explosive cyclogenesis, is often associated with major winter storms and occurs when surface pressure falls by more than about 24 millibars per day. Theoretical analysis has shown that the occurrence of boroclinically unstable waves is directly proportional to the magnitude of the temperature gradient, with maximum growth for wavelengths of 3000 to 5000 km. Wavelengths that are shorter are damped by the horizontal mixing. The 3000 to 5000 km wavelength is the typical separation between high and low pressure synaptic weather system in the middle and higher latitude. Polar fronts and the jet streams. In the troposphere, the demarcation between polar air and the warmer tropical atmosphere is usually defined by the polar front. On the poleward side of the front, the air is cold and more dense. Equatorwards of the front, the air is warmer and more buoyant. During the winter season, the polar front is generally located at lower latitude and is more pronounced than in the summer. Cold fronts occurs at the leading edge of equatorwards moving polar air. In contrast, warm fronts are well defined at the equatorwards surface position of polar air as it retreats on the eastern sides of extratropical cyclone. The equatorwards moving air behind a cold front occurs in poles of dense high pressure known as polar high and Arctic high. The term Arctic high is used to define air that originates even deeper within the high latitude than polar highs. When polar air neither retreats retreats nor advances, the polar front is called a stationary front. In the occulted stage of the life cycle of an extratropical cyclone, when cold air west to the of the surface low pressure center advances more rapidly towards the east than cold air ahead of the warm front. Warmer less dense air is forced aloft. This frontal intersection is called as accumulated front. Without exception, fronts of all types flow the movement of colder air. Clouds and often precipitation occurs on the poleward sides of both warm and stationary fronts, and whenever tropical air reaching the latitudes of the polar front is forced upward over the colder air near the surface. Such fronts are defined as the active fronts. Rain and snowfall from active fronts form a major part of the precipitations received in the middle and high latitudes. Precipitation in these areas occurs primarily during the winter months. The position of the polar front slopes to upward towards colder air. This occurs because cold air tends to undercut the warmer air of tropical origin. Since cold air is more dense, atmospheric pressure decreases more rapidly with height of the poleward side of the polar front than on the warmer tropical side. This creates a large horizontal temperature contrast, which is essentially a large pressure gradient between the polar and tropical air. In the middle and upper parts of the troposphere, this pressure gradient is responsible for the strong westerly winds occurring there. Winds created a lot circulates around a large region of upper level low pressure near each of the poles. The center of each low pressure region is a persistent cyclone known as the circumpolar vortex. The region of the strongest winds, which occurs at the juncture of the tropical and polar air masses, is called the jet stream. Since the temperature contrast between the tropics and the high altitudes is greatest in the winter, the jet stream is stronger during that season. In addition, since the mid latitude also become colder during the winter, while tropical temperature remains relatively unchanged, the westerly jet stream approaches latitude of 30 degrees during the colder season. During the warmer season in both hemispheres, the jet streams move poleward and is located between latitude of 50 degrees and 60 degrees. The jet stream reaches its greatest velocity of the tropopause. Above that level, a reversal of the horizontal temperature gradient occurs, which produces a reduction in the wind speeds of the jet streams of high latitude. This causes a weakening of the westerlies, which increasing height at intervals ranging from 20 to 40 months with a mean value of 26 months. Westerly winds in the stratosphere reverse directions over low latitude so that an easterly low develops. This feature is called the quasi-biennial oscillations QBO. In addition, a phenomena called sudden stratospheric warming, apparently the result of the strong downward air motion, also occurs at the late winter and spring at high latitudes. Sudden atmospheric warming can significantly alter temperature dependent chemical reactions of ozone and other reactive gases in the stratosphere and affect the development of such features as ozone holes. A major focus of weathering forecasting in the middle and high altitudes is the Forecast in the movement and development of extratropical cyclones, polar and Arctic heights, and the location and intensity of subtropical ridges. Spring and fall frosts, for example, are associated with the equatorwards movement of polar high behind a cold front, while droughts and heat waves in the summer are associated with unusually strong subtropical ridges. Effect of continents on air movement. Preferred geographic location exists for subtropic ridges and for the development, movement, and decay of extratropical cyclones. During the winter months in middle and high latitude, the lower parts of the troposphere over continents often serve as reservoirs of cold air as heat is radiated into the space throughout the long high nights. In contrast, the ocean loses heat less rapidly because of the large heat capacity of water, their ability to overturn as the surface cool and become negatively buoyant, and the movement of ocean currents such as the Gulf Stream and the corrosive currents. Warm currents transport heat from lower latitude poleward and tend to occur on the western side of the ocean. The lower troposphere over these warmer oceanic area tends to be a region of the relative low pressure. As a result of this juxtaposition of cold air and warm air, the eastern sides of the continents and the western fringes of the ocean in middle and high latitude are the preferred location for extratropical storms position. Over Asia and in particular, the cold high pressure system is sufficiently permanent that is persistent offshore flow called the winter monsoon occurs. An inverse type of flow develops in the summer as the continents heat more rapidly than their adjacent oceanic areas. Continental areas tend to become regions of relative low pressure, while high pressure in the lower troposphere becomes more prevalent offshore. As the winds travel from areas of higher pressure to areas of lower pressure, a persistent onshore flow develops over large land masses in the lower troposphere. The results of this heating is referred to as the summer monsoons. The leading edge of this monsoon is associated with a feature called the Monsoon Trough, a region of the low atmospheric pressure at sea level. Tropical moisture carried onshore by the summer monsoon often results in copious rainfall. The village of Cherrapunji in northern eastern India, for instance, recorded over 9 meter, about 30 feet of rain in 1 month, July 1861, owing to the Indian summer monsoon. As a result of the continental effect, the subtropical region is segmented into surface high pressure cells in the summer. Large land masses in the subtropics tends to be center of the relative low pressure as a result of strong solar heating. As a consequence, persistent high pressure cells such as the Bermuda and the Azore high occurs over the ocean. The oval shape of these high pressure cells creates a thermal structure on their eastern sides that differs from the thermal structures on the western sides in the lower troposphere. On the eastern sides, subsidence from the headless circulation is enhanced by the tendency of air to preserve the angular momentum on the rotating earth. Owing to the enhanced descents of air over the eastern parts of the ocean, land masses adjacent to these area, typically the western sides of the continents, tends to be deserts such as those found in the northwestern and southwestern Africa and along western coastal Mexico. Effect of ocean on air movement. The arid conditions found along the western coasts of continents in subtropical latitudes are further enhanced by the influence of equatorwards surface airflow on the ocean currents. This flow exerts a shearing stress on the ocean surface, which results in the deflections of the upper layer of water above the thermocline to the right in the north hemisphere and to the left in the southern hemisphere. As warmer surface water are carried away by the offshore ocean airflow, colder water from below the thermocline rises to the surface in a process called upwelling. Upwelling creates areas of cold coastal surface water that stabilize the lower troposphere and reduce the chance of convection. Lower convection in turn reduces the likelihood for precipitations, although fogs and low stratus clouds are common. Upwelling regions are also associated with enriched sea life as oxygen and organ nutrients are transported upwards from the depths towards the surface of the ocean during periods when the intertropical convergence zone is located near the equator. Trade winds from the northeast and southwest converge there. The westward moving winds cause the displacement of the surface ocean water away from the equator such that the deeper, colder water move to the surface. In the central and eastern Pacific Ocean near the equator, when the upwelling is stronger than average, the event is called La Nina. When the trade winds weaken in this region, however, warmer than average surface conditions occur and upwelling is weaker than usual. This event is called El Nino. Changes in ocean surface temperature caused by El Nino significantly affect where cumulonimbus clouds form in the ITCZ and therefore the geographic structure of the headless cell. During periods when El Nino is active, weather patterns across the entire earth are substantially altered. Thanks.